I'm Bryce. I made the video.
I'm Ronnie, and I helped with the report.
I'm Aiden, and I put together the model.
I'm Kyle, and I did the theoretical.
Our objective for this project was to focus on bridging the gap between theoretical thermodynamics and practical engineering by building and testing a functional 3D printed model. Right here is a picture of our model that we 3D printed. It's on one piston. We will first go over the theoretical analysis to understand the principles of converting heat energy into mechanical work. Then we'll cover the construction of and testing of our model. We will end off with our results and analysis for the project.
I'll be talking about the theoretical analysis of a steam engine. The first steam engine was created in 1712 by Thomas Newcomen. James Watt refined Newcomen's invention in the 18th century, allowing it to be used for more industrial applications. I'll be going over how the steam engine works based off of this graphic. The first step in the process starts in the boiler, where the water is heated up, usually by coal or some other kind of fuel, and turned into steam. The steam is then pushed into the cylinder, which houses the piston. The valves are what allows the steam to enter and exit at the appropriate times. The power stroke occurs when the steam enters the cylinder. Steam enters the cylinder and exerts pressure on the piston, allowing it to move. As the steam expands, the piston is pushed away from the cylinder head, converting the pressure energy of the steam into mechanical work. After the power stroke, the exhaust valve opens, allowing the steam to exit from the cylinder. The piston then moves back toward the cylinder head, which is driven by the flywheel. The flywheel is what is connected to the piston, helping smooth out the motion and store excess energy during the power stroke. After this is done, the steam is then turned into mechanical power that is used to drive machinery.
I'll be talking about how I built the model we used for testing, and also how we tested it. As you can see here, it has many different components that all need to be put together using screws, which were provided by my father. All of these parts were 3D printed in the IDEE lab in the Patterson Engineering Building. Once I had all the pieces, I started putting it together. As you can see here, I attached the base to the cylinder holder with 4 screws on the bottom, and attached the cylinder to the cylinder holder using 3 screws. That one in particular inside was a bit of a challenge. The piston then went inside the cylinder through a small hole which you can't quite see there, and attaches it to the piston, which connects to the crank here. And on the side of the cylinder is where the valve goes, and the valve connects to its own crank rod, which connects to the crank. And the crank itself is attached in place by the crank cap right there, which is held on by 4 screws, which at the end of the crank is the flywheel. And of course, during construction there were some issues, mainly having to do with getting the required hardware to put it together. But like as previously stated, my dad came through for me and provided most of the screws. The last 2 screws though, the ones that attached the pistons to the crank, I had to buy off of Amazon. Here we have a video of us testing the model.
There were a few challenges when we were building the model. For example, some parts had to be sanded down to fit. The crank cap and the crank pin both had to be sanded around here and around here. During the construction, we also broke the crank shaft here, so we had to print a new model, and even afterwards we needed WD-40 to make sure that it operated smoothly. On the model there's also some air that escapes, but it wasn't enough to affect the end result.
On our model, we noticed that we can improve, and one of the ways we could improve it was by adding another piston. As you can see on this one has 2 pistons, and our model only has 1 piston, which having 2 pistons would increase the power output. In order to do this, we would have to redesign the whole process using CAD, SolidWorks, and then going in and 3D printing those parts. Another way was using a different material that has less friction. We researched and I found that nylon was a lot better than what we used on here was PLA filament, but nylon would be a lot better because it's a lot more smoother and is a lot more durable than PLA. We could also seal some places in the model, like we said, some air did escape didn't really affect it that much, but if we were able to close those or seal those ports, we would be able to maximize the amount of power that on our model.
In conclusion, this project helped us as a team develop a better understanding of how a steam engine works and how it can be used in more practical settings. The 3D printed model was a great way for us to learn, work together on this project while also learning about thermodynamic processes and how they apply to a steam engine. Overall, we didn't encounter many errors in our project and everything went smoothly and we were able to operate as a team well.